So I am back with the second version of the chapter of solution, second part. Today we'll start with mole fraction of a solution. In class 11 also you have dealt with some of the concentration terms of a solution as to how concentration of any solution can be expressed. One of the concentration term is mole fraction. Mole fraction of any mixture or a solution actually represents the fraction of number of moles of solute or solvent over the total number of the components. For example, if you have a binary mixture or a solution containing only one solute and one solvent, then the mole fraction of solute. In this chapter, properties of solute is mostly marked as 2, like weight of solute will be marked as W2, weight of solvent will be marked as 1, so W1. So for everything of solute we give a suffix 2, so the number of moles of solute is N2, whereas the number of moles of solvent taken here is N1. So to get the mole fraction of solute, what you do is simply divide the number of moles of solute by the total number of moles of solute and solvent. Since you have two components, so the total is N1 plus N2. If you have three components, sometimes in a mixture you have to add the number of moles of all the three components. So X2, which is the mole fraction of solute, is the number of moles of solute divided by the total number of moles of solute and solvent. And similarly, mole fraction of a solvent. How do you get mole fraction of solvent? Divide number of moles of solvent N1 by the total number of moles of solute and solvent N1 and N2. So mole fraction of solvent X1 is number of moles of solvent divided by total number of moles. And since fraction is always calculated out of 1, you know that percentage is calculated out of 100. So if you add percentages of all the components in a mixture, the sum has to be always 100. In the same manner, mole fractions of all the components in a mixture. For example, in our solution we have got only two components, solute and solvent. So the mole fraction of solvent and solute add together must be 1, and it can be easily proved from this simple calculation here. This is the mole fraction of solvent and this is the mole fraction of solute. When we add, you have same thing in the numerator and denominator, which cancels and the sum is 1. So that is X1 plus X2 is equals to 1. So I want you to learn about mole fraction properly, because now we have a situation. The situation is that we've got a liquid here, in fact two liquids. They are different liquids, means they are differently volatile. One of them is more volatile than the other, and now they are in pure state. This is pure A and pure B. In pure state, vapor pressure of any liquid is written as P degree. Whenever you see that degree assigned to the symbol of vapor pressure P, you should understand that it refers to the vapor pressure of the pure liquid. So this is pure A, its vapor pressure is P degree A, and this is pure B, its vapor pressure is P degree B. Now let us assume that both these liquids are maintained at the same temperature. So the temperature is same. I don't want temperature to affect their vapor pressure. So both are maintained at the same temperature. But like they are different liquids, so that's why even though they are maintained at the same temperature, I don't expect both these liquids to exhibit same vapor pressure, because one is differently volatile than the other. So one which is more volatile naturally exhibits more vapor pressure compared to the other one. Now what we do is we'll prepare a mixture of these two liquids. To prepare the mixture of this liquid, what I'll do is I'll take Na moles of A and mix that with Nb moles of B. So it's a mixture of both A and B. There are Na and Nb moles of A and B mixed together. Now once you mix them, what happens is for A, now B acts as an impurity, and you know that impurity always lowers vapor pressure. So the vapor pressure of A will come down because of B working as impurity. Similarly, the vapor pressure of B won't be when it was in the pure state. Now B is mixed with A, so A acts as an impurity, so the vapor pressure of B will go down. So these are the vapor pressures of both A and B when they are in mixed state. So the vapor pressure of A is PA and vapor pressure of B is Pb. Earlier, what was the vapor pressure of A in pure state? P degree A. Now in mixed state, in a solution of both A and B, vapor pressure of A has come down to Pa. So vapor pressure of B also has changed to Pb. We know that because of impurity, vapor pressure always lowers or comes down. That means I know that Pa is less than P degree A. That much I know. I also know that Pb is less than P degree B, because vapor pressure of both A and B has come down. But I don't know how much is Pa. I only know that it is less than P degree A, but I don't know how much is Pa. I know Pb is less than P degree B, but I don't know how much is Pb. But we can get the exact amount or value of Pa and Pb using a law called Rawls law on binary mixture of volatile liquids. So this is the first law we are dealing with in this chapter, called Rawls law on binary mixture. Why binary? Because how many components are mixed here? Two components. Binary mixture of volatile liquids. Both are volatile liquids. So I want to know what is the vapor pressure of A in this mixture. According to Rawls law, vapor pressure of A in this mixture is given by the product of the mole fraction of A in this mixture and the vapor pressure of pure A. You know, when A was in pure state, its vapor pressure was P degree A. So the vapor pressure of A now is given by the mole product of mole fraction of A only and the vapor pressure of A when it was in the pure state. Similarly, according to Rawls law, what is the vapor pressure of B? Vapor pressure of B in this mixture, which is Pb, is given by the mole fraction of B, that is Xb in this mixture, into the vapor pressure of B when it was in pure state, which is P degree B. So do you think it makes sense that this mathematics or simple calculation, is it logical? It's absolutely logical. It's because imagine in this mixture we've got a lot of A. When you have lot of A and less B, I expect A to form a large amount of vapor compared to B. So how much vapor A forms here in this mixture depends on the amount of A, and that's why we have a mole fraction of A here. When you have lot of A, mole fraction of A is high, therefore the vapor pressure of A is also naturally it becomes higher. Suppose you have a very less number of moles of B here, amount of B is less, so its mole fraction will be less and therefore its vapor pressure will be less. So how much of vapor or vapor pressure any liquid exhibits in a mixture of two liquid is decided by its own mole fraction and its vapor pressure when it was in pure state. You can apply this law not just on mixture of two liquids. Imagine a mixture of 100 liquids. So what will be the vapor pressure of 99th liquid in a mixture of 100 volatile liquids? Vapor pressure of 99th liquid will be given by the product of mole fraction of that 99th liquid in the mixture and the vapor pressure of 99th liquid when it was in the pure state at the same temperature. So this is how you can apply Rawls law in order to calculate vapor pressure of any liquid in a mixed state in presence of impurity. Now I just want to extend this idea, the idea of this obtaining how vapor pressure of any component in a mixture in a different situation here. So now I have a single liquid. There's one liquid which is volatile, so I don't have two liquids, so I need not assign A and B. There's a pure liquid, so its vapor pressure in pure state is P degree, and to this liquid now we add a solute, something which dissolves in it, but the solute this time is non-volatile. We are adding such a solute which itself will not vaporize and will not form any vapor. So we don't have to calculate what will be the vapor pressure of the solute, because solute is non-volatile, it's not going to form any vapor. So it's not just non-volatile, it's non-electrolyte. Now what are electrolytes? Electrolytes are substances which dissolves and then splits to form ions. For example, salts like sodium chloride. Sodium chloride splits to form sodium ion and chloride ion. We don't want electrolyte here. We don't want anything which after dissolving splits to form ions. Why not? Because in the formulation of Rawls law, you know, only this fact was taken into consideration, that when you add certain number of moles of impurity, that certain number of moles will have certain number of particles which obstructs the formation of vapor in certain manner and lowers the vapor pressure. So when you add an electrolyte, what happens? When you add 1 mole of electrolyte goes inside and splits to form many number of moles. So your calculations based on 1 mole, you are determining how much of vapor pressure lowering should happen for 1 mole of impurity, but inside what has happened, that solute has dissociated, forming more number of moles of particles, and it will exhibit a different amount of vapor pressure, which will not be able to calculate through Raoult's law. So that's why in all the Raoult's law or any calculation or any theory that's applied to lowering of vapor pressure and other properties of solution, we are supposed to take non-electrolyte, which does not break down to form more number of particles. So we'll add some covalent compounds like sugar, for example, where sugar is non-electrolyte. So when it dissolves, it only splits into same number of particles whatever existed earlier. So we have added a non-volatile, non-electrolyte solute to this liquid. Now what has happened, because we have prepared a solution now it's impure. Because of the impurity, the vapor pressure won't be P degree A. Now vapor pressure of this liquid or the solvent will be lowered. So let's say it gets lowered to a new value called P. The vapor pressure has come down to P. But how much will be that P? I know that P is less than P degree because of lowering, but what will be the value of P? I think we can use this idea of Raoult's law on mixture of two liquids to find the vapor pressure of this solution now containing a non-volatile, non-electrolyte solute. How? Because in this solution, it is not the solute which is forming the vapor. The solution is exhibiting vapor pressure because of the solvent only. It is the same solvent which is exhibiting vapor pressure. So basically when you calculate the vapor pressure of a solution, what you are doing is you are calculating the vapor pressure of which component? It is vapor pressure of the solvent you are calculating. So what will be the vapor pressure of the solvent? Vapor pressure of the solvent will be given by the product of mole fraction of the solvent and the vapor pressure of the pure solvent. When it was pure, its vapor pressure was P degree. Now it's in a solution state, so vapor pressure has gone down. So what will be the vapor pressure of the solvent in this solution? Will be given by the mole fraction of the solvent, that is x1, into the vapor pressure of the solvent when it was in the pure state at the same temperature. So isn't it like this previous one exactly? Because you're finding the vapor pressure of any one component, and that will be given by the product of mole fraction of the same component and the vapor pressure of the same component when it was in the pure state. So here vapor pressure of the solvent should be given by the vapor mole fraction of the solvent itself and the vapor pressure of the solvent when it was in pure state. Now this fact, whatever we have got from here by extending this Raoult's law, is a new Raoult's law. Now we can state it as Raoult's law on vapor pressure of a solution. It is a vapor pressure of the solution which we are talking about. Raoult's law on the vapor pressure of the solution containing non-volatile, non-electrolyte solute. What kind of solute we have got here? A non-volatile and non-electrolyte solute. So how do you state Raoult's law on vapor pressure of a solution containing a non-volatile, non-electrolyte solute? It is stated like this. Vapor pressure of the solution, this is the vapor pressure of the solution, containing a non-volatile, non-electrolyte solute is given by the product of mole fraction of the solvent and the vapor pressure of the pure solvent at the same temperature. That's Raoult's law. So we've got two Raoult's law by now. Okay, so that ends the second Raoult's law, but I want to further expand this mathematical formula. You see, what I want is, I don't want this mole fraction of the solvent to remain here, because whenever we deal with the solution, mostly we find the concentration of the solute rather than the concentration of the solvent. So I want to replace this x1, which is the mole fraction of the solvent, with something of solute. Okay, so you know it's a mixture of solute and solvent. There are two components. So the mole fraction of the solvent plus the mole fraction of the solute, the total has to be always 1. Now what I'll do is I'll try to find the value of x1, that is mole fraction of solvent. So x1 will be x2 minus 1. This 1 goes the other side. Okay. Sorry, 1 minus x2, sorry. x2 goes the other side, so x2 becomes minus. So 1 minus x2. So now x1 is 1 minus x2. I'll replace this x1 with 1 minus x2 here. Okay, so multiply, p degree comes here, and p degree also multiplies x2. I'll bring this p degree other side, it becomes minus, leaving behind minus x2 p degree other side. Now when you multiply both sides by minus, then it will not be p minus p degree, it will be p degree minus p. I just want to remove this minus here by multiplying both sides with minus. So that's what I've done. I've multiplied both sides with minus. So I've got p degree minus p equals to x2 into p degree. What is this p degree minus p? Now look at this. P degree is the vapor pressure of this pure liquid. Let's say it was something around 70 mm. Vapor pressure is measured by a barometer, so as a height of mercury column. So let's say the height of mercury column was 70 mm. So the vapor pressure of the pure liquid is pure solvent is 70 mm. Now since you have added impurity, so the vapor pressure has gone down. So the vapor pressure of the solution now, which is lowered from 70, let's say it has become 60 mm. Okay. So the solution pure solvent has 70 mm of vapor pressure. Now in the solution it is only 60, and this always happens. It's called lowering of vapor pressure. So 70 pure state 70 minus in solution 60. 70 minus 60. What is this? 70 minus 60. Isn't it 10? Isn't it that? Isn't it the value by which the vapor pressure has gone down? Yeah, from 70 to 60 there is a decrease in 10, and that 10 is the amount by which the vapor pressure has been lowered, and that change in vapor pressure, that decrease in vapor pressure is called lowering of vapor pressure, which I'll write as delta P because it's a difference of vapor pressure. So delta P, this is known as lowering of vapor pressure. It's the amount by which the vapor pressure has gone down from pure state to solution. Then I bring this P degree from the other side, it divides here. So this is lowering of vapor pressure compared to the original vapor pressure of the pure liquid. Amount by which the vapor pressure has gone down divided by the original vapor pressure of the pure liquid is known as relative lowering of vapor pressure. Now why relative? Because it's lowering of vapor pressure compared with the vapor pressure of the pure liquid. So whenever we compare any quantity with the other, the term is called relative. So this is lowering of vapor pressure divided by original vapor pressure of pure liquid is called relative lowering of vapor pressure, which is equals to the mole fraction of the solute. Yeah, amazingly this whole thing is equal to the mole fraction of the solute. Yeah, x2 is the mole fraction of the solute. So in a solution, in any solution containing a non-volatile, non-electrolyte solute, the relative lowering of vapor pressure, that means the amount by which the vapor pressure goes down divided by the original vapor pressure of the solution, is always numerically equal to the mole fraction of the solute in that solution. And that becomes the third Raoult's law. We state it as Raoult's law on relative lowering of vapor pressure. So how do you state Raoult's law on relative lowering of vapor pressure containing a non-volatile, non-electrolyte solute? Raoult's law on relative lowering of vapor pressure containing non-volatile, non-electrolyte solute states that relative lowering of vapor pressure of the solution is always equal to the mole fraction of the solute. This formula itself, when you state, that becomes Raoult's law on relative lowering of vapor pressure. So you get this these terms defined in the book also. You got definition in the books. Just follow it, find it and write it. It will be there. So I don't think I should just copy that, write it here. Now I just want to explain some more facts related to this Raoult's law on relative lowering of vapor pressure. Relative lowering of vapor pressure. So for that I have taken a liquid here. Let's say the most common liquid is water. So I have taken a volatile liquid, that is water. How many moles? 3 moles. Now to this water I'll add some number of moles of non-volatile, non-electrolyte solute. So I have chosen glucose because glucose is a covalent compound, it's not a volatile substance, neither it's an electrolyte, it doesn't dissociate. So 2 moles of glucose is added to 3 moles of water. What am I doing? I'm preparing a solution. Why? Because I want the vapor pressure of water to get lowered, because the moment you add impurity and prepare a solution, vapor pressure of liquids will come down. So vapor pressure of water will be lowered. Now what will be the relative lowering of vapor pressure of water? What will be the lowering of vapor pressure of water divided compared to the original vapor pressure of water? This is how you calculate relative lowering of vapor pressure. So let's say vapor pressure of pure water, let's say was 70. Now because you added 2 moles of glucose, let's say it has come down to 50. So the lowering is how much? 70 to 50, 20 divided by the original vapor pressure 70. This is how we find the relative lowering of vapor pressure. But what if you don't know their vapor pressures? Okay, we don't know whether it was 70 in the beginning, now it is 50. You just have to tell me how much will be the relative lowering of vapor pressure of water. How much is relative lowering of vapor pressure of any liquid according to Raoult's law? Isn't it equal to the mole fraction of the solute? And we can easily calculate the mole fraction of glucose here, which is the number of moles of glucose 2 divided by the total number of moles. How many moles total we've got? 2 plus 3, 5. So 2 by 5 is the mole fraction of glucose. And whatever is the mole fraction of glucose, same is the relative lowering of vapor pressure of water here. So relative lowering of vapor pressure of water now is 2 by 5 because that's the mole fraction of glucose. Now what I'll do is I'll take water again, same number of moles. I can take another number of moles, but then it will complicate. So let me just take 3 moles of water. It's pure, it exhibits some amount of vapor pressure. Now to this I'll add another chemically different non-volatile non-electrolyte solute. So I'm adding urea. Urea is a covalent compound, it's non-volatile, it doesn't split into ions, so it will serve the purpose. So I've taken 2 moles of urea. Now because of addition of urea, what happens to vapor pressure of water? Vapor pressure of water gets lowered. But how much? We don't know the vapor pressure of pure water, neither we know the vapor pressure of the solution of urea and water. But what will be the relative lowering of vapor pressure of water? That is lowering of water vapor pressure of water divided by the original vapor pressure of water, which is known as relative lowering of vapor pressure of water. What will be that? According to this law, it will be equal to the mole fraction of urea. That's the solute we have. How do you find the number of moles of urea divided by total number of moles? And now I've taken urea and water in such a way that I want to maintain the same mole fraction. Whatever was the mole fraction in case of glucose solution, same mole fraction I want to maintain. So the mole fraction is again 2 by 5. So what is the relative lowering of vapor pressure of water now? 2 by 5. Okay. Isn't it amazing that in spite of the fact that I have added different substances, one is glucose, another is urea, they're chemically totally different, but water is exhibiting the same amount of relative lowering of vapor pressure 2 by 5 in both the cases. So that means relative lowering of vapor pressure of any liquid will not depend on what you have added. Whether you add glucose or urea or sucrose or fructose or galactose, any non-volatile non-electrolyte solute you add, as long as you add the same number of moles, as long as you have the same mole fraction of the solute, as long as you add same number of particles of solute, the relative lowering of vapor pressure of this liquid water will remain same. It's 2 by 5 here, 2 by 5 here. So this is a property of a solution. Let's say these are both are solution. This is a property of a solution. Which is the property of the solution? Relative lowering of vapor pressure is a property of a solution which only depends on how much you add, how much of solute you add, but does not depend on what you add. Even though you add different things, as long as you have the same number of particles, same number of moles of solute, the relative lowering of vapor pressure of that solution will always remain the same. Such a property of a solution, which only depends on how much of solute has been added and does not depend on what is added, like whether you add glucose or urea, any property of the solution which does not depend on the nature of the solute but only depends on the amount of solute added is called colligative property. So what are colligative properties of solution? They are such properties of solution which only depends on the number of moles of solute added or the amount of solute added, number of particles of solute added, but does not depend on the chemical nature of the solute. Such a property is called colligative property, and one fine example of colligative property of a solution is known as relative lowering of vapor pressure of any solution. Okay.